Good morning, Geo. Here's what we're going to work on. We just got done with our Unit 10 test. We're going to go Unit 11, which is all about circles, okay? First off, you're probably wondering, why do you have a triangle drawn here, right triangle? Second of all, why are you telling me to use trig, okay? So this is a little warm-up for today. We want to use trig to solve for a missing side length. So pause the video, draw that out. Try it out. Remember, we're trying to use sine, cosine, tangent. All right. Label our sides. This is the adjacent side. This is the hypotenuse. So if you remember back in the day, we did SOHCAHTOA. Since they gave us the adjacent side and the hypotenuse, we're going to use the one that has the adjacent side and the hypotenuse. So we would go the cosine of 22 is equal to 10 over x. And then from there, we would solve. I'm going to get out my trusty calculator, right? We would cross multiply. That's how I would suggest you do this. So then we would multiply x times cosine of 22. Actually, I don't need to get out my trusty calculator because, and then divide both sides by the cosine of 22. And then, since I have my calculator, let's see here, Desmos. You have a little time to think. Remember, you want to go up to the top, hit the wrench. I'm going to do a projector mode so you can see a little better. We want to be in degrees. And then we have 10 divided by the cosine of 22, which is about 10 point, we'll round out to 10.8. Okay, there's a method for my madness on why we did this, okay? So that's just a little review of trig, picking sine, cosine, tangent, labeling the triangle, all that kind of good stuff, right? All right, so let's get into circles. What do we got? Well, we have covered this year a radius, diameter. We've even talked about the circumference of a circle and the area of a circle, right? Now we got some new words that we're going to throw at you today. And we'll talk about that. So first off, the definition of a circle is just a set of all points that are equidistant from a specific point. We call that the center of the circle. All right. So all these points are the same distance from the center of that circle. So it's just a set of all points that are the same distance away. All right. To name a circle, we name it by the center. The center is J. So we can draw a little circle symbol, circle J. Okay? A chord, something that you play with on a guitar, right? The different chords that you play. Well, in geometry, a chord is a line segment whose endpoints are on a circle. So we got our chord. All right, we're finding two spots where our points are on a circle. And the chord is the line segment, okay? Line segment. So that's an orange, so I'll keep this in orange color code. We would name it by calling it line segment AC. So chord's endpoints are out in a circle, all right? Then we'll go to diameter. It's a specific chord. It's a chord that goes through the center, right? So it's endpoints, so we got the diameter. Its endpoints are G and D, and it is on the circle, and it goes right through the center. So line segment GD. All right? Radius, in this case. Line segment with one endpoint at the center and the other on the circle. So we say always set half of the diameter. So the radius starts at the center, goes to the end, or you can go the other way around, go F to J. Either way, it doesn't matter. And then now we have two other new words that we're going to talk about. The first one is a secant. A secant is a line array that intersects a circle in two places. Well, I don't know what happened here at the end. In two places. So it's like a chord. The chord goes through, a chord has its endpoints on the circle. A secant goes through and intersects, right? So we have the secant is the entire line that crosses. Or you could say the ray right? Ray, start at C and go all the way, say, or likewise start at A and go this way. So it's more than just the line segment. It has to go through and extend in at least one direction. So we would name that one with the arrows. Start at one of the points and go through with the ray, or start at the other end point and go through to make the ray, right? And a tangent intersects the circle in exactly one spot. We're going to talk specifically about tangents today, okay? So that would be line XM or MX, all right? So those are our new words. We're going to focus mainly on tangent today. Throughout the week, we'll be talking about chords and some other good stuff. So those are new circle terminology. All right, let's go ahead. Pause the video. Put your word to the definition here really quick of what we just talked about. All right, segment with one endpoint on the center and one endpoint on the circle. That is what we call the radius. Segment whose endpoints are on the circle. That is the chord. A line segment or ray that intersects the circle in exactly one spot. We call that the tangent. Tangent intersects in one spot. And segment that goes through the center, that's the diameter. The locus or set of all points in a plane equidistance, that's the definition of a circle. And a line or array that intersects a circle at 2 points. Intersects, right? Not whose endpoints on the circle, but intersects. That is the secant. All right. Quick review. So here we go. We have some properties of a circle. So the first thing, the theorem is if a line is tangent to a circle, okay? So if this line is tangent to a circle, and we could tell because it intersects it in exactly one spot, okay? Then it is perpendicular to the radius. Well, we talked about last week what perpendicular meant. Perpendicular means intersecting and forming 90-degree angles. Weird. So why would he have us work with trig? Oh, because we have a right triangle. It's crazy, right? Crazy how all this stuff is coming full circle again. See what I did there? Oh my gosh. I am on fire. All right. So we know that if it's tangent, it's perpendicular, right? If it's tangent, then it is perpendicular. All right. Likewise, if it's perpendicular, then it's tangent. Okay. We're going to go there. So in the example we have, and in words, a line is tangent to a circle if and only if it is perpendicular to a radius, right? So we have our picture down here, line L, right? You could use that little thing, or you could do Y, T, X, whatever, any combination of those points, okay, and call it a line. It's tangent to circle L if and only if line L is perpendicular to the radius, which is ST. So if they give us tangent, we have a right triangle. Now we can use our right triangle math, Pythagorean theorem, and trig to our benefit. STX, that's 90 degrees. The point of tangency is at T. All right. Second property. If two segments from the same exterior outside points are tangent to a circle, then they are congruent. So what that's saying is we have this point outside or exterior of our circle. It is the same distance away to these two spots right there, causing it to be tangent to those two spots, causing those two segments to be equal. All right, and if those two segments are equal, then we can say that they are tangent, which then forms this little picture, right? This is drawn in there. That's 90 degrees. This is drawn in there. That's 90 degrees. Oh, and these are two, our radiuses are the same. So really what we just drew is a kite. Weird looking kite, but it's a kite. Okay? So if QP and RP are tangent to circle C, then QP is congruent to RP. And then we get to write that down here. All right, so we get equal information and we get 90-degree information if we get tangent. All right, so let's apply our knowledge. All right, so use the diagram below to answer the following questions. MC and MZ are tangents to circle. So MC, so I know this distance right here is congruent to this one. I also know if they're tangent, I have the right angles here, which has right triangles, right? So find the measure of BCM. Well, we just put that in there. BCM, B to C to M. That's 90 degrees because the tangent and the tangent line and the radius are perpendicular. Okay? Number 2, find the length of CM if, well, CM is congruent to ZM. So I'm going to make a little equation. They wrote it backwards, that's why it was tricking me up. 5x minus 9 is going to equal the other segment, because that's also tangent. And then we would subtract x. 4x minus 9 equals 7. Add 7, 4x equals 16. X equals 4. All right, and it says find the measure of CM. And then we got 5 times 4 minus 9, which is 11. All right. Again, we set them equal to each other because the two segments came from the same point, M, and it was tangent to both points, so those are the same. Find the length of E to M if CM is 12. Oh, I like this problem. All right. So we'll highlight, since we got lots of stuff going on. Find the length of EM. If CM is 12 and BC is 5. All right. Well, we have a right triangle. Okay, and I'm just going to draw it right here. Oh, drew that terribly. All right, but we do have a right triangle. There we go, that's better. The right angle's over there. So this is 5, this is 12. Now what we're going to do is we're going to find the hypotenuse. Okay? We're going to find the hypotenuse. This guy here. Because what we know is if we find that length, we know B to E is 5. We want to find E to M, so we could just subtract that off. So we're going to do the Pythagorean theorem quick. 5 squared plus 12 squared equals C squared. All right, 25 and 144 gives us a grand total of 169 equals C squared. Square root of both sides gives you C is equal to 13. So this whole length is 13. The length of B to M is 13. Well, we just want E to M, so we're going to do 13 minus 5. And that gives us this bad boy, E to M is equal to 8. Like that question. Get you thinking a little bit. Pythagorean theorem and circles all together. All right? So now CBM is 60. CM is 13 times the square root of 3. We could type that into the calculator. It'll give us decimal. Find the length of BC. All right. So CBM. I'm going to erase this whole mess here. C to B to M. That's 60. All right. And then it's giving us CM is 13 radical 3. Find the length of BC, which is this length here, okay? So I'm going to draw our triangle again. That's the 90. That's 60. This is 13 radical 3. And we want to find BC, which is this length right there. We'll call that X. Well, this is where we're going to use trig. This is why we went over it. This is the opposite side. That's the adjacent side. Sine, cosine, or tangent. We are going to use tangent. So we would say the tangent of 60 is equal to opposite 13 radical 3 over adjacent, which is X. And then we would solve X times tangent of 60 equals 13 radical 3. And then divide, and we get 13 radical 3 over tangent of 60. All right, so we're going to go clear that out. We're going to go 13 square root of 3, divide, whoa, all right, 13 square root of 3. Well, maybe we'll just divide it by. And then tangent of 60. We're just going to play around with this so it looks the way we want it to. We're going to delete that guy. Go back on top. All right. Now we are good. Weird, it's 13. Yes, there is an easier way to get the answer, but we didn't have time to go over 30, 60, 90 triangle. So we use trig because trig will get us where we need to go. Right triangle math is either trig, Pythagorean theorem. Okay? So the length of BC is 13. We did that using trig. All right. Find the length of CM. If BC is 12, BM is 20. Right? So if I draw my right triangle again, BC is 12, BM is 20. Well, this time I'm giving you the hypotenuse, so we'll go 12 squared plus b squared equals 20 squared. And then subtract 144 to both sides. So we got 400 minus 144. So we have b squared is equal to 256. And then the square root of 256, 16. Yahtzee, we're rolling. And then find the length of XE, which is the diameter, right? So again, being able to pick out the picture, that's the diameter. If BM is 25, all right, so they're going to give us BM, and they're going to give us ZM. What the heck am I going to do here? I want to find the diameter. I have a right triangle. Okay, I have this right triangle right here. They give me BM 25 and ZM is 20. I want to find this value here, which is the radius. How do I find the diameter if I know the radius? Multiply by 2, right? So we're going to do a squared plus b squared equals c squared. And then we'll get 625. Subtract the 400, b squared is equal to 225. And the square root of 225 is going to give us 15. So I just found the radius. B to Z is 15, right? I just found this length, BZ. I want to find two of those. So 15 and 15 is 30. So XE equals 30. All right, so that's just using those properties, right? So again, the markings we get to put, because it says tangent, we get to put the radius. The tangent line makes the 90-degree angle should be on the inside. It flip-flopped there for some reason. That looks kind of weird out there, all right? So those are the markings we get to put in. Theorem number 2 we talked about is if one point outside of the circle is tangent to two different spots, then those two line segments are congruent, so the outside pieces are congruent. Again, we get to draw the radius in there on both sides, and those two values are going to be congruent too because they're both a radius. And then we didn't talk about the circumscribed polygons, but basically tangent on the outside, if you draw everything tangent so it cuts through the circle one time, then we have a bunch of little extra. It's applying the same property, this property, 4 different times. So rock on, guys. Nice job. Circles today, circles tomorrow. Enjoy.